Good afternoon, everyone. Uh, I'm very glad to participate in the Climate Resilient Agriculture for Asia 18th TSAE International Conference. I want to say thanks for giving a chance for me to participate uh, in that conference for the organizer. In that part, I'm going to talk about numerical study of thermal behavior in flat plate solar collector system. And flat plate solar collector is a device that absorbs the solar radiation on a flat surface and transfers the captured heat to the working fluid, usually water, air, or something like that, flowing through the tubes attached to or embedded into the surface. The In the next part of the presentation, the geometry and thermal boundary condition are demonstrated. Water, is used as heat transfer fluid in modeling of the flat plate solar collector. And additionally, black coat copper surface is used for the absorbent plate, which enhances the absorption of the solar radiation and improves the overall thermal efficiency of the system. The transparent cover of the solar collector is made of the glass, allowing maximum solar radiation to enter while minimizing the heat loss to the environment. Polyurethane foam is employed as the insulation material, which effectively reduces the thermal losses and helps maintain the desired temperature with the collector. The simulation were performed under the steady-state condition. The following parameters were used in the table table 2 and table 1 and table 2. And the material properties of the system is given in the table 1. The geometric dimension of the flat plate solar collector is demonstrated in the table 2. And we have used finite element analyzer for modeling. The finite element analyzer is a numerical computational method used in engineering and scientific research to model and analyze complex physical processes. Finite element method is widely used to solve the differential equation and analyze an environment with complex geometries. The geometric generated mesh for the flat plate solar collector is provided in the figure 2. And we have selected one Kathmandu 3D point for providing the result in the output section of the flat plate solar collector. And the number of elements for the finite element solver is demonstrated in the table 3. And the mesh characteristics is consisted of the number of elements, triangle elements, quad elements, edge elements, vertex elements, average element quality, and element area ratio, mesh volume also investigated. And we have used this equation for modeling. The Comsol multiphysics we have used heat transfer in solid and fluid interface and laminar flow interface in the Comsol multiphysics. And for the heat transfer fluid, we have used first and second equation. For heat transfer in fluid, we have used 3 and 4, 5 and 7 equation we have used for fluid. Let's turn to the results. And in the figure 3, you can see the outer and inner surface temperature variation of flat plate solar collectors. You can see the outer surface is lower than the inner one because as I have mentioned, inner surface made of the black coated aluminum, and it can gain more heat just to enhance the thermal performance of the flat plate solar collectors. And we have simulated the system at 4 different velocities, inlet velocities. And in the four different inlet velocity, you can see the surface temperature variations of the flat plate solar collector. The maximum surface temperature variation is observed with lower inlet velocity at 0.3 meter over second. And the result is we have analyzed the Reynolds cell number, convective heat transfer, Prandtl number of the system by inserting the mathematical equation to the variable part of the Kamsel multiphysics. And you can see the Reynolds cell number. The Reynolds cell number is higher at a higher velocity. Prandtl number is higher at a higher inlet velocity. Convective heat transfer at 3 different inlet velocity has also demonstrated. The maximum convective heat transfer value is observed with the higher inlet velocity 0.4 and 0.45 meter over second. And temperature variation at 4 different inlet velocity also has demonstrated, and the maximum temperature variation is observed with the lower inlet velocity at around 0.3 meter over second. And useful energy gain also, you can see the useful energy gain is higher with the higher inlet velocity. And I mean at 0.45 meter over second inlet velocity, the useful energy gain is higher. I mean that in that side the water is gaining gathering the more heat with the time. Just let's turn the conclusion. In conclusion, this study contributes to fundamental understanding of heat transfer process in flat plate solar collector. Critical parameters such as fluid flow behavior, temperature distribution, convective heat transfer rates, and useful energy gain with a flat plate solar collector are numerically analyzed in Kamsel multiphysics. The simulation revealed that the temperature distribution across the plate exhibited special variation at inlet velocity of 0.3, 0.35, 0.4, and 0.45 meter over second. It was observed that lower flow rate enhanced the efficiency of the heat transfer between the absorber plate and circulating fluid, leading to the higher outlet temperature of the flat plate solar collector. This behavior underscored the intricate relationship between the flow velocity and thermal performance, highlighting the role of reduced flow velocity in optimizing thermal transfer efficiency with the solar collector system. That's all. Thanks for your attention.